Okay, ladies and gentlemen, in this episode we're going to take a look at magnetic flux linkage, and what's the difference between those, and how this leads us to Faraday's law of electromagnetic induction, which is the basis for how we actually generate electricity. So let's get to it. Okay, so let's remember our way back to our last lesson where we were looking at magnetic field strength. The idea was that the magnetic field strength of a magnet was simply its magnetic flux density, which was how many of these little lines could you fit into a particular area. So if I had, say, a little circle, let's fill it in, okay, and I placed it at particular points, then the magnetic field strength at that point would be equal to the number of field lines, or the amount of magnetic field lines that would travel through that circle. And this is why your magnetic field gets weaker at certain points and is stronger at other points. Okay, this was magnetic field strength. Okay, and we had this equation that B was equal to phi divided by A, where B is the magnetic field strength measured in Tesla, phi is the magnetic flux measured in Weber or Webers, and of course our old friend A for area measured in meters squared. And we use this as a definition to try and understand what magnetic flux was. And it simply is a case of it's a measurement of the number of field lines that you get traveling around a particular magnet. And if you had a total value of phi, you would know the total number of field lines that would be generated by a particular magnet. Now, since magnetic fields are infinite in range, then phi is theoretically an infinitely large number, which is why we have it confined to a particular area. We want to know how much phi is there in a particular area in meters squared. Okay, and this is magnetic flux. All it tells you is about lines. Well, that's great, but we want to use this now for electricity purposes, rather than just for gathering stuff and lifting stuff with magnets and going, oh, well, there's the strongest part of the magnets at the poles. And we can visualize that now. And we know it's because of the fact that there's more flux per unit area at the poles of the magnet than there are, say, along out here, that there's less flux per unit area out here. That's great. But cast our mind back to the generation of AC electricity, either at GCSE level or at lower 6th level. What we knew about that was that in order to generate electricity, we could get one of these things, which is a solenoid. Essentially, it's a series of wraps of wire, coils of wire, wrapped around some form of little hollow box. Right? And as we brought a magnet closer to it, we got some current, maybe a light bulb lit up. As we moved away, we also got some current, which was weird, and the light bulb lit up. And what we got was, as we moved backwards, forwards, backwards, forwards, backwards, forwards, we got current traveling. Okay, we got current that was going one way and then the other way, and then one way and then the other way. We didn't quite explain why this was. We maybe explained it in terms of electrons traveling and then not traveling, but let's understand what's actually going on here. That as the magnet travels towards this coil of wire, the magnetic flux starts to travel through these coils of wire. And I'm going to make this transparent so that we can actually see what's going on. So let's transparency that. As I travel through, let's watch this particular coil of wire. As my magnet approaches, there are no lines of flux in this little coil of wire. As we come in, suddenly a couple of lines of flux find their way in. There's 1, 2, 3 lines of flux are now inside this coil of wire. And then as we come a little bit closer, we get 1, 2, 3, 4, 5 lines of flux. And then we've got 1, 2, 3, 4, 5, 6, 7 lines of flux. And as we move in, we get more and more and more lines of flux that are traveling through this coil of wire. And as we come back out, that number decreases again, back down to eventually 0 once my magnet is far enough away. Okay, this is why electricity travels inside coils of wire with magnets moving near them. Okay, and it's got to do with something called flux linkage. That it is all about how much magnetic field is traveling through a particular coil of wire, and more importantly, how quickly that number is changing. Okay, so rather than talking about total flux, because if I've got the coils, the flux traveling through here, I've got 1, 2, 3, 4, 5, 6, 7, 8 lines of flux inside this coil. It's utterly irrelevant to me then how many other lines of flux there are available in this magnet. I'm only interested in what's going on here in this particular coil of wire. The amount of flux that is coming through a coil of wire at any given time is called the flux linkage for that coil. So it's the amount of flux that is being caught, as it were, by that coil of wire. So imagine that the coil of wire, let's draw it in a slightly more transparent way. So that's a coil of wire, imagining we could see through it, that as we bring it towards our little magnet, more and more lines of flux are being caught. Think of it kind of like a magnetic catching net, like catching butterflies. Okay, and then it catches less and less out here, and it catches more and more in here. This is what flux linkage is. Okay, and that's fine. For a single coil, flux linkage is just the amount of flux that's traveling through that particular coil. But for an entire solenoid, the flux linkage is how much flux is actually being captured by all of the coils. So if we have this one here, we have 1, 2, 3, 4, 5, 6, 7 of these coils are all catching flux. So rather than just saying there's 1, 2, 3, 4, 5, 6, 7, 8, 9 lines of flux being caught in total, that's not true, because this coil is catching 1, 2, 3. This one is catching 1, 2, 3, 4. This one's catching 1, 2, 3, 4, 5, 6, maybe 5, maybe 6, and so forth. So the number is different for that. And even if we had a perfectly uniform magnetic field, which let's draw one to make life a little bit simpler. If we had this completely uniform magnetic field traveling in through here, then each of these coils of wire would be receiving 4 lines of flux. Let's assume that each line of flux is a Weber. Then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and you get the point. That we'd have to count up all the lines of flux going through here. And that would be rather tedious. But we do have some advantages. Okay, the first thing we could do is we could actually apply some maths to it. That we already know that the total amount of flux, phi, is equal to the magnetic field strength B multiplied by the area A, as a simple rearrangement of B equals phi over A. Because we know that B equals phi divided by A, we can write that phi, the total amount of flux, is equal to B multiplied by A, where in this case A would be the area of a single coil. B remains the magnetic field strength of our field, and for the sake of argument for the rest of this, we're going to assume that our magnetic field strength is nice and constant. It's nice parallel lines of magnetic flux. We can do more complicated stuff later, but we'll deal with nice parallel lines here. Okay, so what we would then be able to say is, well, the total amount of flux traveling through this particular coil is the flux density, or the field strength, B, multiplied by the area A. That would give me my total flux. But I don't want my total flux. I want the total flux that's traveling through all of the coils. So what I'd have to do is I'd have to count up how many coils are being affected by this flux, and then because of the fact that we've got a nice consistent field, because B is a constant here, we can just simply multiply that by N. Okay, and this is the flux linkage. This is the total flux linkage, and it's written as N phi equals BAN. And this is the flux linkage for a coil. This is the total flux linkage for a series of coils. Okay, not phi. Phi is the flux. N phi. So phi is the flux through a single coil. N phi is the flux linkage for the whole lot of them. Okay, and this is an equation that you have to know. That n phi equals BAN. So n phi equals BAN, with n phi being the flux linkage, B the magnetic field strength in Tesla, A the area in meters squared, and N the number of coils of wire that are being affected by this flux. Okay, now let's put this into some form of actual equations so that we can see what we're playing with here. So we have a magnet of uniform field strength, 6 millitesla, is moving towards a series of 800 coils of area 1.25 meters squared each. What we want to do is we want to calculate the total flux linkage of the coils. Okay, so nice and simple then, we have that n phi is equal to B times A times N is our equation we want here. Okay, so we have 800 coils. Now we don't want to put the 800 in here because we're trying to calculate n phi. Okay, so n phi, because it doesn't get its own, well it does but not yet, it doesn't get its own symbol. So we have n phi equals 6 by 10 to the negative 3 times 0.125 times 800. n phi here is what we're trying to calculate. Okay, we're not trying to calculate phi, we're trying to calculate n phi. 6 by 10 to the negative 3 because it's 6 millitesla, 0.125 because it's 0.125 meters squared, and 800 because it's 800 coils. And that gives us an answer for n phi equal to 0.6. Now, the question is, what is the unit? Now, we can work the unit out by doing dimensional analysis on this side, or we can just look at n times phi. N is the number of turns of wire, so therefore it has to be a pure number. Phi is the amount of magnetic flux measured in Weber, so that is then unitless times Webers, which gives us a flux linkage of 0.6 Weber. All right, and that is wonderful and interesting and great maths, but ultimately still of limited use to us until we put it in to our next concept. Remember what we said earlier, that in order to make this this little light bulb light up, what we're going to have to do is we're going to move this magnet towards and away from this solenoid. If I just set it, even inside it, the light stays off. However, if I withdraw the magnet, the light comes on briefly, and as I move it in, the light lights up. Provided the magnet is moving, I'm going to get some form of current traveling through here. I'm going to get some form of light happening in my little light bulb. Now, why is that? Well, the first reason is conservation of energy, that I simply can't get energy for nothing, so I can't just set a magnet here and expect energy to come flowing out of it. That would be somewhat foolish. Okay, so work has to be done. But more importantly, it is to do with the fact that the amount of energy or the amount of EMF you get, and hence the amount of voltage that we end up with, is equal to not the flux linkage, but the rate of change of flux linkage. Okay, that the fact that this little coil here currently has no flux traveling through it, and now it has 3, and now it has 5, and now it has 7. The fact that the flux linkage is changing through that coil is what generates the electricity. It's what generates the EMF. And the fact that it's then going from 7 down to 5, down to 3, down to 1 on the way out is also a change and will also generate electricity. And this was Faraday's great insight, was that flux linkage by itself was interesting, I suppose, but the really interesting bit was that the amount of EMF produced was directly proportional to the rate of change of flux linkage. And that is Faraday's law, and we need to be able to state it. Faraday's law says the EMF produced is directly proportional to the rate of change of flux linkage. Written in its truest form then, we have that E for EMF is equal to the rate of change with respect to time, so that's the d by dt of flux linkage, n phi. Now, a few of you might be having a slight panic if you're not doing A-level mathematics. So don't worry about it, because A-level physics doesn't require you to be able to differentiate this. Because in the situation where the rate of change of flux linkage is consistent we can simply put this as over t. It's a bit like acceleration is the rate of change of velocity with respect to time, that you could write that acceleration is equal to the d by dt of velocity. But we can also say that a equals v over t if we want the average acceleration, or we simply accept the fact that the velocity is changing steadily. Okay, either of those is fine. Either of those is fine. So we will write that E, the EMF, is equal to n phi, the flux linkage, divided by t, the time taken for that change to occur. So we have the EMF E in volts, n phi, the flux linkage in Webers, and t, the time in seconds. Right, so we need to be able to use that. We need to be able to use that and figure out what is going on here. So let's have ourselves an example. So our example says a magnet of uniform strength 0.4 millitesla is moved through 700 coils of wire of area 0.09 meters squared in a time of 200 milliseconds. What is the average EMF induced? Okay, so what we want to do then is we want to use that EMF is equal to n phi divided by t, and we simply plug the numbers in. So E equals 700 multiplied by, oh no, we don't appear to have phi, but we can go over here and calculate n phi, because remember that n phi is equal to BAN. So n phi equals 0.4 times 0.09 times 700. So n phi equals 25.2 Weber. So we can remove our 700 here and return that into 25.2. Divided by our time interval, which was 200 milliseconds, so that's 200 times 10 to the power of -3. Putting that all into our calculator yields a final EMF of 126 volts. Easy as that. All right, so that's the basics of electromagnetic induction and how it works. In the next one, we're going to take a look at Lanza's law, which actually slightly improves upon this equation and allows us to work out the direction of the magnetic field that's created by our solenoid, the direction of the EMF that is created, and hence any induced current that might happen. But that's for the next time. In the meantime, what we've got that the EMF induced is equal to the flux linkage for n coils divided by the time taken for that flux linkage to occur. Okay, that EMF is equal to the rate of change of flux linkage. And it's simply due to the fact that we need lines of flux traveling through coils of wire and then traveling out of those coils of wire in order for us to generate electricity. Okay, thank you so much for your attention. Your homework is linked in the description below. And all that remains for me to say is that, as usual, physics rocks. It's true.